Good evening and welcome to our Astronomy Talk series in partnership with the SETI Institute. Tonight's program, Searching with NASA's SOFIA, a flying stratospheric observatory for infrared astronomy. My name is Lisa Hoover, Programs Manager here at Chabot Space and Science Center, and I will be your host for tonight's discussion. We're thrilled to bring yet another exciting virtual program direct to your homes. Our guest tonight is Dr. Dana Backman, NASA Airborne Astronomy Ambassador. He will help us get to know SOFIA, which recently helped scientists find water on the moon. And from SETI tonight, the SETI Institute, we're joined by Dr. Stephen Steele, Director of Education and STEM Programs, with a few words to set the stage for tonight's program. Welcome.
Thank you very much. And Simon, my evil twin, Stephen, couldn't make it tonight, but that's okay. Welcome. Good evening, everybody. This is the 7th joint SETI Institute Chabot Talks for Families. This is something we've been doing since last August, working with our friends across the Bay. Just to say a little bit about the SETI Institute, we are a non-profit research institute located in Mountain View, California. We are dedicated to the search for life in the universe in all its forms, everything from microbes on Mars all the way up to advanced alien civilizations. Please do check us out on our SETI Institute website, seti.org. And you'll be able to see a lot more about the research that's done with our scientists. Please also take a look at either the SETI Institute's YouTube page or Chabot's YouTube page, where all of the previous talks in this series are located, so you can catch up with all of the great stories and the great science that's been done. I'm going to stop now and hand back to Lisa to hear a lot more about the SOFIA Observatory. Thank you very much, Lisa.
Thanks, Simon, and welcome to all of our guests out there. If you're in the chat, why don't you let us know where you're watching from? And by all means, if you have questions for Dr. Bachman, put them in the chat and we'll get them to him and answer as many as we can. Dr. Bachman is the principal investigator of NASA's Airborne Astronomy Ambassadors Program. He has a Bachelor's of Science in Physics from MIT and a Ph.D. in astrophysics from the University of Hawai'i Infrared Astronomy post-doctoral research program at the Kitt Peak National Observatory in Tucson, Arizona, and at NASA's SearchAmes Center. Professor of Physics and Astronomy for 12 years at the Franklin and Marshall College in Lancaster, Pennsylvania. He's been employed by SETI as a Director of Education and Public Outreach for NASA's Stratospheric Observatory for Infrared Astronomy, SOFIA, at the NASA-Ames Research Center from 2003 to 16. He's taught numerous courses on introductories to astronomy at the Santa Clara University on global climate change at the Stanford University's Continuing Studies program, and he's co-authored with Michael Seeds of 3 college introductory astronomy textbooks, Horizons, Foundations, and ASTRO. Just a reminder, while you're watching his presentation, if you have questions, put them in the chat, whether you're on YouTube or Facebook, and we'll get them to Mr. Bachman. So without further ado, I turn it over to you.
Hi, everyone. I'm going to share my screen and some slides, and thank you for the invitation to talk to you this evening. Let's see if I can. Are you seeing my slide? Yes?
Seeing the slide, but slide mode. Perfect, Dana.
There we go. Okay. So what you're seeing here is SOFIA, the Stratospheric Observatory for Infrared Astronomy. And in the course of my talk, I hope I can convince you that it might not have been a crazy thing for NASA to buy a used 747 airliner and cut a hole in the back, put a rollback door on it, and then install a 17-ton telescope. Why would anyone do that? That's more or less what I'm talking about, and what has it gained us? So I work at the SETI Institute in Mountain View with in fact, Simon as my boss, and my desk is at NASA-Ames that I haven't seen for 11 months. And I'm very happy to be invited to give this talk for the Chabot community. So what the topics, I'll talk about infrared light and infrared astronomy first, a little bit of background information, and then how SOFIA operates, and then some of the highlights of what SOFIA has managed to discover in the course of its operation so far. So what I'm showing in this slide is a sort of a cartoon of something that actually happened in the year 1800. This is William Herschel, who was the astronomer who discovered the planet Uranus about 20 years before this. And he had quite an interesting life history. He started out as a classical musician and composer. He was born in Germany, moved to England, and he was a choir director and chamber music director and composer. You can hear his chamber pieces on KDFC if you listen for a while. And so sometime along in there, he picked up a book on the mathematics of astronomy. Well, he picked up a book on the mathematics of music first, and was so fascinated that he picked up another book by the same author on the mathematics of astronomy, and changed careers. He became an astronomer, and in fact, one of the world's most productive astronomers of the late 1700s and early 1800s. What you see in the background is the large telescope in his backyard. This actually the window wouldn't have been open for this experiment. So that's why it's sort of a cartoon. But he and his observing partner, Caroline, his sister Caroline, explored the northern hemisphere skies with that large telescope on his property. But what you're seeing here in this cartoon is an experiment he did to let light through a prism on the wall, sunlight, and onto the spectrum onto the table. And then he's moving around a wooden stage with thermometers to measure the intensity or the ability to heat up the thermometers of the different colors of sunlight. He wanted to know if some colors were more capable of heating the thermometers than others. And he's got a control thermometer outside the sunlight beam to monitor the temperature in the lab. Well, at the moment that you see in the picture, he's pushed the thermometers past the red to where the human eye doesn't see any sunlight color, but the thermometers still detect sunlight. So he's pondering the fact that there's a color beyond red that the thermometers are responding to, but the human eye can't see. And so he named it infrared. That's his term, which means beyond red or below red. And so this is the discovery that there's such a thing as invisible light, as paradoxical as that might seem, in the year 1800. Now, more than 200 years later, we know that there's all sorts of types of radiation that correspond to light that are the same kind of phenomena as light, but that your eyes don't see, like X-rays, microwaves, radio waves, ultraviolet. All of those are the same physics, the same kind of wave as a light wave, but human eye can only see a narrow slice of the electromagnetic spectrum. Well, now, this is, when we get to the mid-1900s, 1960 or so, we get to where astronomers are starting to observe the sky with infrared detectors in addition to visible light cameras. And now this is not from the 1960s, but by 1983, there was a satellite, a small space telescope called IRAS, IRAS, Infrared Astronomy Satellite, that was a joint American, Dutch, and British project. And this on the right is an image of part of the sky. Well, it's an image put together from IRAS data of the region around Orion at a wavelength of 60 microns, which is considered far infrared. It's the human eye sees wavelengths from 0.4 to 0.7 microns, and that's the picture on the left, is with a camera sensitive to the same kind of light that the human eye can see. And you see in the picture on the left, most of what you're seeing are objects around the temperature of the sun, a few thousand degrees or a few tens of thousands of degrees. And on the picture on the right, the infrared picture, that's material that's only a few hundred degrees, 50 or 100 degrees Kelvin, several hundred degrees below zero Fahrenheit, 300, 400 degrees below zero Fahrenheit is the material that's glowing in this picture on the right. And the bright yellow patches are star forming regions where hundreds or even thousands of stars are condensing out of dense parts of the interstellar medium. So you see with the ordinary camera or your eye, you're seeing the stars. In here, there's a whole dramatic other universe that can be seen with an infrared camera. And in particular, star formation. That's one of the things that infrared observatories can see because this material is colder than stars and doesn't make visible light, but does make infrared light. So when I teach this at Santa Clara University, the students would challenge me and say, well, Professor Backman, I can't see infrared, so how come I can see that picture? Well, it's a representation. Here's an example. Here's a baseball stadium with the price of the tickets colored. So the highest price tickets are red. The next highest price tickets are this sort of orangish tan, and then light blue, and then purple. And so it's just a way to represent numbers by colors. This is an image of a supernova remnant, a bubble of gas blown out into space by an exploding star. And in this case, the intensity of the radiation, someone decided to make orange be the most intense and purple be the least intense radiation in this bubble. And that's an arbitrary choice. There's no rule that says you have to make the intense part orange and the low intensity part purple. You could do the other way. It depends on what you want to bring out. So this is what's sometimes called false color, but I think a better term is representational color images. Sort of a nice combination of art and science to represent something that the human eye can't see so that you can see it, and how you do it is a sort of a little bit of an artistic endeavor to represent the invisible to the eye. Well, anyway, so what does an infrared observatory like SOFIA, what can it do in particular? Well, as I already said, infrared telescope and camera can detect things that are cooler than stars. And an example are stars and planets forming and the raw material for stars and planets to form. Also, interstellar dust clouds, they're opaque to visible light, but they're transparent or relatively transparent to infrared light. So with an infrared camera, you can see inside the dust clouds or through them, and to see what's on the other side of interstellar clouds. Even something as powerful as the Hubble Space Telescope, with using visible light camera, can't see through an opaque interstellar dust cloud, but an infrared camera can. And also then the fingerprints, the spectral fingerprints of large organic molecules tend to be at infrared wavelengths. And that might surprise some of you that there's organic compounds in space, but there's lots and lots. Organic doesn't mean biological, but organic large carbon molecules are found in all sorts of contexts in outer space. And then another thing that SOFIA can do, because it's mobile, not because it's an infrared observatory, but it can observe things like solar system objects crossing in front of background objects, and you can only see that from certain parts of the Earth. SOFIA can go to remote parts of the world and see events that are only visible in certain places and not all over the world. Now I'm going to stop and see if there's any questions in the chat.
Yes, there is a question from Joel. Wants to know your opinion of, hopefully I'm pronouncing it correctly, Ayumatha?
Oumuamua.
That one.
Yes, my opinion. It's exciting to me because it's the first known interstellar object. The people who are trying to claim that it's an alien artifact, there's no reason to believe that at all. And I think some of these people are professionals, and I'm ashamed of them. They're you know, it's a disgrace. So it's an extremely exciting, interesting object, and the way it was detected, there are probably 100 of them at any one time within the orbit of Neptune. It's not an exceptional object at all. Now that we know how to find them, we're going to find many of them, and there's no reason whatsoever to think it's an artifact or a spacecraft, but it is an interstellar object, and that's incredible. Okay, so there's my rant for today.
We have another question from Joel. Wants to know, are the star forming regions we're seeing from billions of light years away still forming stars presently?
Those are only 1,000 light years away, so that's a blink of an eye. All of that you're seeing in that picture there, that's about 1,000. It's 1,500 light years away, so it's basically current right now. 1,500 years is nothing on the scale of this. So yes, all of those star forming regions are forming stars right this moment. Shall I go on?
Yes, and guests, if you have other questions, put them in the chat. We'll get them to the doctor.
Okay, I'll remember to stop in a few more slides. Okay, so now this is a little bit of a complicated, busy plot, but what it's showing is different kinds of radiation and whether they reach the ground or they get stopped by the Earth's atmosphere. So what you see, this is the entire electromagnetic spectrum, all the different kinds of quote unquote light. Gamma rays, low short wavelength, high energy, X-rays, ultraviolet, visible light, a very small slice, as I said, of what is possible, infrared, microwaves, and radio waves. Gamma rays, X-rays, and ultraviolet mostly don't reach the ground. They get stopped by the Earth's atmosphere. Some ultraviolet gets to the ground and can give, a sunburn or a tan. But if all the ultraviolet that the sun put out reached the ground, it would be fatal to go outdoors. So most of it's blocked by the atmosphere. Visible light obviously gets to the ground from space. Some infrared does, some does not. Some of it's blocked mostly by water vapor. And then radio waves mostly reach the ground. So a radio observatory can be on the ground and do fine. A optical observatory can operate on the ground, but infrared observatories need to be off the ground, even in space, and X-ray, gamma ray, ultraviolet observatories also. This is specifically about infrared, which, as I said, is blocked mostly by water vapor. But the water vapor in the Earth's atmosphere is mostly confined to the troposphere, the lowest layer of the atmosphere. And this boundary here that you're seeing is the boundary between the troposphere and the stratosphere, called the tropopause. So 99+% of the water vapor in Earth's atmosphere is in the troposphere. And if you can get into the stratosphere, there's almost no water vapor above you between there and space. So infrared, if you can get your infrared telescope up into the stratosphere, it's almost as good as having it in space. And hence the Stratospheric Observatory for Infrared Astronomy. Here's examples of a ground-based observatory and a space infrared observatory. Some of the telescopes on Mauna Kea are specialize in some infrared observing, an infrared that reaches the ground. This is Mauna Kea, altitude of 4 kilometers, 13,700 feet. And Hawaii, this is where I did my graduate work up here. It's a fantastic place. And this is Hualalai, a volcano in the background. These are the Keck telescopes and so on. So the Spitzer Space Telescope was a satellite carrying a telescope that was put into solar orbit in how come I can't remember what year it was launched? 2003, I think. And this is about a 32-inch diameter telescope that was cooled almost to absolute zero. So this gets far above the Earth's atmosphere. This situation here is easy to get to, but doesn't have access to all of the infrared coming from space. So you have SOFIA as the compromise. Think of it as a low-flying space telescope that comes home every morning. This is about a 106-inch telescope, 2.7 meter diameter telescope behind the rollback door. This is one of the early test flights of SOFIA to test the door. This is it's a NASA and German. It's a U.S. and German project. It's 80% NASA and 20% German. That's the German Space Agency, DLR. And in fact, at this moment, SOFIA is in Cologne, Germany, for a 6-week science campaign following a 3-month preventive maintenance visit to the Lufthansa maintenance yards in Hamburg. So, yeah, so Germans are a substantial partner with the U.S. on operating SOFIA, and SOFIA is sitting in Germany right this moment. So it's so 2.5 meters or 2.7 meters is a little bit of a quibble, because the diameter of the aperture is 2.7 meters, 106 inches, but the secondary mirror only looks at 2.5 meters of the telescope for reasons to optimize it for infrared use. But anyway, the airplane is based at NASA Armstrong facility, which is near Los Angeles at the edge of the Mojave Desert. But the science center, most of the scientists are at NASA-Ames up here in the Bay Area. The first science flight was in December 2010. We're still ramping up to 120 science flights per year over what's hoped to be a 20-year lifetime. And for 1 to 2 months a year, SOFIA goes down to New Zealand to use the Southern Hemisphere winter sky. So it's Northern Hemisphere summer, Southern Hemisphere winter. SOFIA is based at Christchurch, New Zealand's airstrip. And it gets a lot of very good science from observing objects that can only be seen from the Southern Hemisphere. So SOFIA works, it has the 747 SP aircraft, which is a special model of the 747 that has a shorter fuselage and longer distance flight than the regular 747. We're flying at above 39,000 feet, which puts us above most of the commercial traffic. And it's a 17-ton reflecting telescope. very similar in size to the Hubble Space Telescope, but this comes, as I said, it comes home every morning and we can tinker with it instead of having to mount an entire space shuttle expedition to go swap out parts when the Hubble Space Telescope has a tummy ache. And then we have a set of scientific instruments that can be used to make the measurements. I'm going to stop now and wait and see if there are more questions.
There certainly are. While we're speaking about the spacecraft, here's one. At 40,000 feet, how much, if any, danger are the various forms of X-ray radiation to the crew aboard the SOFIA?
We're still below the altitude. We're still at an altitude where the X-rays and gamma rays and most of the ultraviolet don't reach the ground because they're stopped by the ozone layer, which is at about 50,000 to 75,000 feet. So the ozone layer blocks the high energy radiation, and SOFIA is flying below that. If we flew at 50,000 feet, that would be a problem, but we're at an altitude where that's not an issue.
All right. What's the most exciting object you've observed with SOFIA?
Well, I was on board SOFIA when the lunar water observations were made, and that was big fun. Although I'm an astronomer, I haven't used SOFIA for my own research. I've been since I came on the SOFIA program, I've been employed managing this program that bring high school teachers on board SOFIA so they understand how the scientists do their job. And I'll talk a little bit more about that later. But my favorite observations that SOFIA has made, but not by me, are, well, the lunar observation, but also the center of the Milky Way galaxy. And I have a slide to show that later. So,
all right, we have a couple of more. One of our 7-year-old viewers wants to know, could an infrared telescope see a black hole?
A black hole itself is dark. It doesn't give off light, but an infrared telescope can see the material around the black hole, especially if the black hole is inside or behind interstellar clouds. And that's the case with the monster black hole that's at the center of the Milky Way galaxy. So I have a picture of that, and because SOFIA's infrared cameras can see through the intervening the dust clouds that are between us and that we get a view of that nobody else can.
That's great. One of our guests is wondering, have you ever seen anything unexplained in the universe?
I'll if we have time for I was working as making research observations at Cerro Tololo, which is in Chile in South America. It's foothills of the Andes Mountains, and we had finished my project a little early, and so the telescope operator Francesco and I were standing outside on the platform that's at the summit of the mountain, just enjoying the beauty, waiting for the sun to come up. And then I noticed something going overhead that was moving at about the speed of a satellite, but it zigged and zagged like a water bug, kind of zig and then zag and then zig and then zag. And that's not a satellite. Satellite can't do that. So I don't know what I was seeing, but I looked at Francesco and he looked at me and we both said, "You see that?" "Yeah, I see that. I don't know what that was." So I guess the simplest explanation is that was some kind of satellite maneuvering, changing its course, but it changed course like 3 or 4 times during a minute or two that we were watching it. And so I don't know what that was, but there's probably a simple explanation.
Fascinating. One more, and then we'll let you continue on.
Okay.
Is SOFIA coming to Christchurch this year?
Probably. We didn't go last year because of COVID. New Zealand completely closed down to any visitors from outside. But at this point, we're expecting to go back to New Zealand about the 1st of July for 6 or 8 weeks. Yes. Okay. So I'll go on and then pause again. So here's a cutaway view of the inside of SOFIA. So there's a bulkhead here that the telescope is behind this. So here's the telescope at the back. Maybe you can see my cursor. And the astronomers and other personnel are sitting at consoles here in a shirt sleeve environment. So we're not exposed to the outside air when the door is rolled back. And the telescope brings its light through this bulkhead down this pipe, and then the camera or spectrograph that's analyzing the light is right here, where it can be accessed by the scientists if they want to. And the scientists are sitting at a console here. The telescope operators are here. There's a mission director who is coordinating all of this and communicating to the cockpit crew. And then the teachers that I bring on SOFIA sit at a console that's right here. So this one of the 6 instruments is on here, and they don't change during one night. They're usually on for 2 or 3 weeks, and then you swap the instrument. It takes a whole day to take one of these big cameras off and put another one on. They weigh 500 to 1,000 pounds, so it's not an easy thing to pull them off or put a new one on. Okay, so I'm going to try and show you a video. Let's see how this works. Stop share. Okay, now if I try sharing again, where are you all? One moment. Share screen. Are you seeing a SOFIA?
Mm-hmm.
Okay. This is a video taken from a chase plane, a small plane following SOFIA to watch how things were going. And this is at twilight, and here is the door opening. Now, you would think you open a door that big in the side of an airplane and the maneuvering would get really funky, or you'd have a terrible noise like blowing on a Coke bottle for 10 hours. But no, we can't tell inside. We have a readout that says the door has opened, but there's no way to tell. And the pilots say it handles just like an ordinary 747 without a hole, which is what we wanted. It's nice to know that it works that way. So I'll stop share and I'll go back to my slide. So we only open the door at full altitude. It's not opened at ground level, and we close it before coming back down. And so I hope I'm back to my slide set. Yes. Okay, yes, so here's an animation of the light coming from a star down to the main mirror, bouncing off a secondary mirror to a third mirror that splits the infrared light from the visible light, and the infrared light goes down the tube through the bulkhead to the camera or infrared instrument that's here, and the visible light goes down here to another mirror, and then we have a camera that lets us look at the visible light and lets us aim the telescope to make sure that we're pointing at the place we want to be. Let me run that again here. Light from the star down to the main mirror, bounces up to a secondary mirror, bounces down to a third mirror that splits the light to infrared and visible light beams. And then the visible light beam goes to a guider camera, and the infrared light goes to this camera or spectrograph that we've got. So here is another view, and this is a little complicated, but here is the bulkhead here at the middle, and the cabin is to the left, so that's where we're sitting. Here's the telescope. The light comes, bounces 3 times and goes down this tube to the camera that's mounted here at the end of the tube. So you point the telescope first by turning the airplane to the heading that it needs to be, and then the telescope is floating on a big bearing, this big sphere that's embedded in the bulkhead. There's gyroscopes to sense its position, and then the optical TV cameras that we have a software feedback loop to make sure that we're pointing at the whatever object it is we want to be studying. So let me stop again and see if there's questions at this point.
Yes, we have a few. Here's one. I think the question is, how much time does it take SOFIA to collect an image?
Well, it's usually, well, some of the images, well, it's a little complicated, but exposures are 1/10 of a second. So there's 10, sometimes 10, as many as 10 images per second. But those images, those keep going for could be half an hour, 2 hours, and then added together in a computer once the flight is over. So I think the question is sort of how long does SOFIA spend studying any one object in the course of a night? And sometimes it's half an hour, sometimes it's an hour, sometimes it's 2 hours, something like that. So maybe half a dozen or 10 objects in a night will be studied on a SOFIA research flight.
Wow. Here's another question. When SOFIA's doors open, is the crew exposed to high atmospheric winds or temperatures?
No, we're protected. It's I'll show you a picture in a moment, but we can't even tell that the door is open. We're in a normal pressure in the cabin of the aircraft, and the telescope with the open door is behind a pressure bulkhead, and so we're not exposed to that at all.
All right, one more before we move on. How long does SOFIA operate during an 8-hour flight?
Well, so actually, normally it's a 10-hour flight, and 8 hours of which we're doing astronomical observations. So it's an hour to get up to altitude, open the door, get set up, and then start working, and then an hour after at the end of the flight to close down, check everything out, and come back down. So 10-hour flight, 8 hours of which we're doing research.
All right, that's all we have for now.
All right, onwards. So here's the set of different instruments that can be put onto the SOFIA telescope, which serve different purposes and are useful for studying different kinds of objects. This forecast is a camera that was built at Cornell. FPI Plus is a camera that was built at the University of Stuttgart in Germany. This is XES, it's a spectrometer, so it takes spectra. It was built by the University of Texas, but then the team that did that moved to University of California, Davis, and that's where they are now. You see the scientists and engineers who built it, they're standing, so for scale, you can see how big one of these is. And this is a great spectrometer. That's an acronym. The first word is German, but anyway, this is built at the Max Planck Institute in Germany. FIFI-LS was built at the University of Stuttgart, and Hawk Plus was built at the University of Chicago, and then NASA JPL in Los Angeles. And so these different instruments, each one would be on for 2 or 3 weeks, and then you swap out and put a different one on and use that for 2 or 3 weeks, but you don't change them during a night. So the astronomers who are doing research with SOFIA specifically ask for one of these, and then they get their observing time when that instrument is on the telescope. This is what it looks like on board. And when I'm on board, I always have the illusion that I'm facing forward, but everyone here, we're facing back to the back of the airplane. This is the bulkhead, the wall the telescope is behind. This is the forecast Cornell-built infrared camera with the gold electronics box. This red can with the gold box. That's the forecast camera. Here are the scientists. Here are the telescope operators. And I'm taking this picture standing up, looking over the top of the teacher console, looking towards the back. Okay, so you see the questioner who asked, is the crew exposed to the outside? You see everybody's just chilling in their sweaters and jackets. It's a little cool on board, but not cold, and we're not being sucked out the hole. No, it's a environment. It's noisy and it's a little cool, but it's not a violent situation at all. And here's two typical flight plans. So leaving from Palmdale, California, and going out over the Pacific, and each zig in the zigzag here is looking at a different object. So looking at one star or galaxy, and then looking at a different one, and then a different one, and then you come home. So you can see how many, there's 4 or 5 objects. This is a flight plan. So it's hard to see. This is the west coast of the US. This is Baja California. Here's Mexico. This is Idaho, Wyoming. And then here, this was a flight plan where we left from Palmdale and we flew as far northeast as Minnesota, and then came back to Palmdale at the end of the night. These are both perfectly normal, and the flight path has nothing to do with what's on the ground. They are determined by what objects are being studied. And I've been on a flight plan where we went to northern Yukon, Canadian Northwest Territories, and we saw a wonderful aurora display from the plane way up there. Yeah, but anyway, so these flight plans, this is quite a complicated business to calculate a flight plan that gets a bunch of objects that the astronomers requested to be observed, taken care of, and then get home at the end of the night with some fuel left in the plane. Okay, so now I have some examples of SOFIA science, but before I do that, I'll stop for questions again for a minute or two.
All right, let's see. Here's one. How are the observing targets held steady despite the aircraft cruising and other random fluttering?
Excellent question. So first of all, the telescope is floating. It's suspended on a double spherical oil bearing with an oil layer in between the two spheres. So the telescope, all 17 tons of it, is in a sense floating on this layer of oil. And then there are gyroscopes to sense its orientation, and then there's push-pull pneumatic mechanisms to push it to the right position, and then we look through the guider camera, this visible light camera, and you sort of put a crosshair on a star that's near the target you're studying, and then there's the software program keeps it steady, keeps the crosshair on the target or the nearby reference star. So telescope is suspended so it doesn't feel the vibrations of the plane. And the software system senses the orientation of the telescope, and then we fine tune that with this visible light camera and software feedback system. I hope that answers the question more or less.
Yes. Next, we have a question. Does SOFIA support gravity?
Yeah, we're at full normal gravity. I wonder if the question comes from wondering if we're the NASA zero gravity airplane, which does parabolic trajectories, and while the plane is going up over the top of the trajectory, everybody's weightless for a few minutes, well, actually more like 30 seconds on board. It's how they train people to understand their own reactions to weightlessness. No, on SOFIA, it's normal gravity. It's being on a passenger airplane. We're not the so-called vomit comet.
I guess this follow-up question, is there any gravity wave event analysis?
Oh, no, we're doing infrared, and SOFIA is not it's not able to detect gravity waves. That's somebody else. That's a whole different complicated kind of observatory, completely unlike SOFIA, that would do that kind of research.
Could you tell us a little bit about SOFIA's range in terms of distance and angle?
Distance, let's say distance and what? Pardon?
And angles?
We can see, if I understand the question, we can, SOFIA can, the telescope can look from 20 degrees above the horizon to 60 degrees above the horizon. So it can't look straight up. So it's a range, and it only looks out the left side of the plane. So the angle that we can, so it's a limited range of elevations. So what you have to do is either wait for the Earth to turn for your object to come within that range of elevations, or turn the airplane so that the telescope's pointing in the right direction, and then the telescope, so SOFIA flies about 5,000 miles in the course of a night, and as far as you can get, so 2,500 miles out and 2,500 miles back would be the maximum range. I don't know if that was the range that the questioner was interested in, but.
Hey, thanks. We have a few more.
So,
if they found water on the moon, is there fossilized or the possibility of dormant life in the water?
The water and the moon, I'll get to that, but the water on the moon is in the form of just isolated water molecules embedded in grains of the dirt. So there's no reason to expect life on the moon. The water is not accumulated in any particular place. But so sort of the answer is no. But I'll give you a little bit more perspective on the lunar water in a few slides.
All right. And a question about Mars. It's all on our minds right now.
Yeah.
Can SOFIA be used to observe the Martian moons, Phobos and Deimos?
Yes, it can. Hasn't been yet. No astronomer has proposed that, but SOFIA could observe Phobos and Deimos, and SOFIA can and has observed Mars itself. So yes.
All right, and where can we find pictures taken by SOFIA?
If you go to the SOFIA, just Google SOFIA spelled with an F. You got to spell it with an F, not a PH, and then disambiguate the capital of Bulgaria. And then you'll go to the Science Center website, and then it has media and public as one of the menu items. And then you have a whole gallery of SOFIA images and information that SOFIA has gathered, and it's presented for the public or for reporters on there. So just go to the SOFIA Science Center website, which is I'll rattle off the URL, but you can get it from a search. It's www.sofia.usra.edu. Okay.
All right, we'll let you carry on, and we'll catch up with the rest of these questions in a little bit.
All right. So now here is on the right is the very first image that SOFIA made on its first science flight in 2010, in May 2010. And when I say image, it's actually 3,000 images that were put together in a computer in a software to make this composite false color or representational color image of Jupiter. And this is a visible light image of Jupiter at the same, more or less the same side of Jupiter at about the same time. And what this shows, so this is a composite of 3 different wavelengths, 5.4, 24, and 37 microns wavelength. Remember that the human eye sees between 0.4 and 0.7 microns wavelength. So this is much longer wavelength radiation than the eye can see. Anyway, what scientists knew before this was that Jupiter puts out more heat than it receives from the sun. It's a net source of heat radiation. What the SOFIA image shows very plainly is that the heat is coming out of Jupiter not uniformly, but especially in this latitude stripes. This white stripe is where there's a copious amounts of heat coming out of the interior of Jupiter, and it's the same place where there's an upwelling that's bringing these orangish brown organic substances from deep inside Jupiter. So the infrared image shows the heat coming from inside Jupiter, and the visible image shows the organic compounds coming from inside Jupiter. So to really know what's going on, you have to put these both together. But that was a very first science flight of SOFIA, getting to be 11 years ago now. Now about Mars. So methane is a substance that is produced on Earth almost entirely by living organisms, by the metabolism of bacteria or basically bacteria metabolism, and it's not produced by, it's much less often produced by non-biological processes on Earth. So if you see methane on Earth, it's almost always coming from biology. Now there's an astronomer, Mike Mumma, and his colleagues at NASA Goddard who took spectra from the Earth-based observatory on Mauna Kea in 2008 and noticed that there was methane in Mars's atmosphere. And it was not at places in Mars's atmosphere where, on Mars, where there's volcanic activity on Mars, which is the likely other explanation for methane. So this was a big deal. Are we seeing, the results of metabolism of bacteria in the Martian environment? The Curiosity landed in a while ago. Gee, I don't remember. It's like 5 years ago. Maybe somebody knows that better than I do. Not off the top of my head. But the Curiosity rover detects occasional bits of methane blowing past it in the breeze, and not all the time, and only in certain seasons. So as a ground-based detection, but then there's a probe, a European Space Agency and Russian probe, ExoMars, orbiting Mars and examining Mars's atmosphere, and doesn't see any methane. So there's detection from Earth, which was kind of marginal. Curiosity detects methane once in a while. This orbiter doesn't see any. So SOFIA is going to be used to monitor Mars's atmosphere for methane over the course of, a long period of time, over the course of many seasons, to see if we can detect it from SOFIA. So this is an open question, and very, very interesting question, but that SOFIA can help address and add to the information. Now, here's a completely different thing. If you have an object in our solar system like Pluto that is in the foreground, relatively speaking, to a background star, if Pluto moves in front of a background star, then there's, in essence, a shadow cast on Earth that lets us study Pluto's properties by the properties of the shadow. And we can put SOFIA into the shadow where this shadow might be in the middle of nowhere, and where there's no observatory, but our flying observatory can maneuver itself into the shadow. So this is called an occultation, where Pluto or some other object in the solar system blocks the light temporarily of a background star. This is how the rings around Uranus were discovered by SOFIA's predecessor observatory called the Kuiper Airborne Observatory. Was flying in the middle of the Indian Ocean, observing Uranus blocking a star, and they discovered that there were rings, 5 rings around the planet Uranus that blocked the star before the planet did. And so that's the kind of thing that a flying observatory can do. So this is Pluto was known to have a faint atmosphere. And what the atmosphere of Pluto does is it makes its edge fuzzy. And so that as Pluto moves in front, from our point of view, of a background star, the edge is not sharp. There's a sort of a fuzzy edge to Pluto, and so the light gets blocked gradually instead of rapidly. And this is a track in the year 2015. This is where the shadow of Pluto went across the Earth, right across New Zealand, where SOFIA happened to be based at that time. Nice coincidence. And you see the middle of the shadow track and the edges of the shadow track. So this is the diameter of Pluto, which is almost the same size as Australia. So there's your trivia for the day. Pluto and Australia are roughly the same size. Okay. And so SOFIA took to the air. There weren't any large observatories in this part of the world, even on the ground in New Zealand. And SOFIA positioned itself right in the middle of where the shadow was traveling 50,000 miles an hour across the surface of the Earth. And here are the data. So this is the brightness of the star, and then Pluto gets in front of it and blocks it, and the light from the star diminishes, but not immediately, but gradually, because Pluto's atmosphere gives it a soft edge. Then now here is the star completely blocked by Pluto, and then in the middle of this, for a few seconds, the star right behind Pluto, from our point of view, makes Pluto's atmosphere light up as a ring for a few seconds, and then it fades away, and then Pluto uncovers the star, and the brightness of the star comes back up to its normal value. So this is like 2 minutes for this whole thing to happen, and this was the observations made. But this central flash, what's called, was an indication that there was a fairly dense atmosphere around Pluto, surprisingly, because in 2012, the same observations were made, and I happened to be on that flight, fortunately, and there was almost no central flash, even though SOFIA was positioned correctly. And so it appeared that Pluto's atmosphere got denser from 2012 to 2015, which is a complete surprise because Pluto's going away from the sun, and so the atmosphere should be diminishing, turning into snow and collapsing. So we had 3 weeks before the New Horizons spacecraft got to Pluto, we had information that Pluto seemed to be active, that the atmosphere had gotten denser from 2012 to 2015. And lo and behold, the New Horizons images show all sorts of signs of geological activity, cryolava flows, burying mountains and covering craters, and so on and so forth. So we had the clue that the New Horizons people, hey, look out, you might see that there's signs of activity when you get to Pluto, and lo and behold, 3 weeks later, they did. So I see that I'm close to the amount of time that I'm supposed to take here, but I've only got maybe half a dozen more slides to go, so you'll indulge me to continue. This is I referred to this earlier as one of my favorite images. This is a Hubble Space Telescope image of the center of the galaxy at a near infrared wavelength. So you can sort of see through some of the interstellar dust clouds. And this is a cluster of stars at the center of the galaxy. And in the center of this, invisible in this image, is the supermassive black hole, 4 million times the mass of the sun at the center of the Milky Way. This is a SOFIA image of the same scale, of the same spot. There's nothing in common between these two images, basically. This is stars here on the left. This is a donut of material orbiting rapidly around the supermassive black hole, and you see the white streamers. That's material peeling off of the inside of the donut and pouring down into the black hole, which is about where my cursor is. You can't see the black hole. Somebody asked, can you see a black hole with SOFIA? No, but you can sure see its effect on the surroundings. And that's what's here. So like I said, this is one of my favorite SOFIA pictures. The drama, all of the drama in this scene is in the SOFIA image, and the Hubble image is just kind of, so what? So this is big deal about studying the supermassive black hole and its environment in the center of the Milky Way. Now I'm getting to the moon observation. So I took this picture with my cell phone on the left from our monitor on the teacher console of the moon, of the piece of the moon that was being studied with the spectrograph. This is the science console, at a slightly different piece of the moon. But here, this is being used by the telescope operators to make sure we're pointing at the place the scientists wanted to study, which is near the crater Clavius. Now, it was already known that there's water in the form of ice in the bottom of shadowed craters at the moon's south pole. The L-Cross satellite impacted in one of those craters and threw up a plume of vaporized ice, water vapor that was detected. And so we knew that there's ice in particular, cold storage, dark craters at the south pole of the moon. This is not there. This is somewhere else, and it's not everywhere on the surface of the moon. The scientists who did this experiment compared different places on the moon, and there's a large region where there's water detectable in the soil, but not other places it's not there. So it's in some places and not others. The amount of water, so I think there was a question that bore on this earlier. If you had a cubic yard of moon dirt, so a cube 3 feet on a side, pretty big box of moon dirt, there would be 1 water bottle's worth of water in that. That's how much they measured to be there. People at NASA headquarters were very happy with SOFIA about this because the people thinking ahead to putting a human base on the moon, you might be able to extract the water for the base from the soil. It's not like there's enough water for a swimming pool, but you can extract water from the soil and not have to carry it to the moon. So here's my last slide. So I am basically done. So what I do for most of my job is recruiting and training high school teachers that I bring on board SOFIA so that they can understand how the scientists do their work and then take that information back to their classrooms. Here's a group of teachers and then 2 district science people that I had, the 4 teachers and the two district liaisons and me outside SOFIA after we had landed at the end of the night. So we got off the plane and we're having a group picture, but this is where we were on board. This is the teacher console. And here are the teachers. And I think I didn't take this picture because this is the back of my head sitting here. You see, we have headsets on because it is very noisy. And so we talk on the intercom headsets. But this is a dedicated console for the teachers, and the scientists and the engineers are at these other consoles. And then the telescope is at the back here. And I think I'm done. So I can take questions for a while. I'm happy to go as long as you want me to go.
All right, well, we've got the questions in queue. First one, why isn't SOFIA affected when the door is open?
It's a very good design. One of the things is that the fuselage has a slight swelling upstream forward of the telescope door, so that the air traveling along the skin of the plane jumps, sort of like a ski ramp, jumps over the opening and then comes back to reattach behind the opening, so that we don't get a vortex, a whirlwind inside the telescope chamber. And so the tests that this would work were done at the wind tunnel at NASA-Ames here at Moffett Field, that if you had a 747 with a hole that size behind the wing, that it would fly okay, that the aerodynamics would be okay. I guess it's not obvious, but they had to do wind tunnel tests on models of SOFIA, found that it was likely to be okay, and then, yeah, it works. Hey, you probably wouldn't guess that this would work, except there was a smaller airplane with a smaller telescope that preceded SOFIA, and they sort of had the idea of that, but then they scaled it up for SOFIA.
Wow, that's amazing. Let's see, our next question is, what are some of the future plans for SOFIA, say in the next few years?
Well, SOFIA, what we observe with SOFIA is what astronomers request. So there's what's called a call for proposals every year, and astronomers in the US and Germany submit these sort of, they're like little research proposals, grant proposals. And then we convene a panel of astronomers to judge these proposals. And then the good ones, the most exciting ones, get those astronomers get to use SOFIA for the observations they request. So we can't tell. We don't know ahead of time what is going to be observed. It's what astronomers have decided, and we get surprised, like the astronomers who proposed the moon observations. Nobody thought that was something that SOFIA could do, but the staff said, okay, let's give it a try. So we know that SOFIA is going to be doing observations of stars, galaxies, and planets, but we don't know what, because it's going to be whatever the astronomers request, and that gets a high grade in the proposal process. But the bigger picture is that SOFIA is on this rhythm of 10 months of the year based in California and 2 months of the year based in New Zealand, and that we expect that to continue.
And any plans for upgrades over the next decade?
How you upgrade SOFIA is not upgrading the plane or the telescope, but making the instrument a new camera, which is even more sensitive than the cameras that we already have. So a new instrument. So NASA has a plan to, as the current instruments get older, to replace them with newer and better instruments. And so you can think about this: if you have a more sensitive, a better camera, it's like having a bigger telescope without making the telescope bigger. So that's part of the plan, and that's the virtue of SOFIA. We don't have to, like a Hubble Space Telescope, send up a space shuttle crew to put in new cameras and take out the old cameras. Just SOFIA sitting in its hangar down in Palmdale, we can have astronomers build a new camera that's better than the one already on, put that on, and then we have a better observatory.
Wow. We have a follow-up clarifying question from an earlier one on the distance. The question is, what's the reach of SOFIA? How far can it detect objects?
Depends on how bright an object is, right? A supernova explosion, which is the brightest thing, the brightest single object that you could have in the universe, SOFIA could see one 10 billion light years away. So the question needs you to say what thing we're looking at and then how far away it would be. However, SOFIA doesn't usually do long distance cosmology research. Most of SOFIA's research is either inside our solar system or inside of our galaxy or nearby galaxies. So this might be a little disconcerting, but astronomers consider a nearby galaxy anything closer than 10 million light years. That's nearby. So that's sort of the normal range of SOFIA is just only 10 million light years, let's say.
All right. Another Mars question. Will the Perseverance rover be sensitive to or be able to detect methane signals?
You know something? I just realized as I was talking about Curiosity, I don't know if Perseverance has an atmosphere testing instrument on it or whether it's only testing the soil. It's a great question, and I honestly don't know the answer. I hope there is.
I guess we'll find out.
Yeah.
Next question. What instrument on SOFIA was used to observe the occultation?
It's the FPI plus. So it was maybe I can go back to that slide. Let's see. Oh boy. Stop share. Hang on a second. Oops. Here we go. Start share.
Not yet.
Okay, how about now?
Yes.
This one, FPI Plus, is the one that did the, it's a high-speed photometer, so it measures brightness very rapidly, repeatedly. And this was what did the Pluto occultation.
All right, next question. How can you be sure, this goes back to an earlier image as well, that you're seeing the ring of a molecular dust at the center of the Milky Way instead of some other cloud of dust in front of it?
Because we can tell from the, because it's unique. That ring is, there's nothing else like it in the galaxy, and it's held in its position. It's the speed that the material is moving at tells you how much mass is inside the ring, in the center of the ring, and there's nowhere else in the galaxy where there's that much mass in one place. So the only place where that structure could be is at the center of the Milky Way, because it needs the gravity of the black hole and to be stable. And the black hole is we have ways of detecting, of being sure where the distance to the black hole, 8.5 kiloparsecs, 25 million light years, 25,000 light years.
All right, we have a lot of inspired students watching this evening. How does one become an astronomy ambassador?
Well, the teachers, well, we want, so what you'd have to do, we recruit school districts now, not teachers directly. So what you need to do, if you're a teacher and you want your teacher to be one of our flying SOFIA teachers, get your school district to contact me, and you can Google me at or look at the SETI Institute webpage and find my email address. So have somebody in the school district office contact us and we'll work out an agreement that will bring teachers from that district on future SOFIA flights.
All right. Can you do something like a virtual tour aboard SOFIA for students?
I can't. I thought there was one on YouTube. Maybe it's been taken down, but yeah, I think you can find one. Look for SOFIA Observatory and look for a virtual tour. Also look on the website, the Science Center website, www.sophia.usra.edu, and find a virtual tour there.
Okay. What's the more logical explanation about the existence of water on the moon?
The water is, there's two different rival explanations, and they're not sure about this, but one of the possibilities is that there's a little bits of water vapor coming out of mild volcanic activity at some spots on the moon, and that so there's a little bit of water vapor coming out of the inside of the moon, and then it ends up being embedded in the soil. That's one possibility. Another possibility is that there's hydrogen coming from the sun in the solar wind, and it's bombarding the lunar soil and combining with already oxygen and hydrogen that's already there and making water that way. And I think the first explanation is got a little more evidence in its favor. So the water, the current explanation, as I understand it, is that the water in the soil was ultimately coming from inside the moon by volcanic vents of some sort.
All right, we have two more. Did SOFIA catch a glimpse of a neutron star's collision alerted by, is it LIGO, back in 2017?
No, because let's see, we weren't looking at the right place at the right time. LIGO can detect the gravity waves, but SOFIA could examine the debris, the expanding cloud of stuff from that collision. And I don't know if any astronomers have proposed that observation, but we could. Not the collision itself. You'd have to be incredibly lucky, but the aftermath could be something that SOFIA could study.
All right. And besides teachers, can civilians be guests on SOFIA?
Not really. We've had lots of reporters who've flown, some of them who were from the hometowns of the teachers. But anyway, the people who were not actually staff members, scientific or engineering staff of SOFIA who've flown have been teachers and journalists, reporters, and a few members of Congress and their aides to check out whether the taxpayers' money is being spent well. So that's sort of the list. We can't take anyone under 18 because it's classified as an experimental aircraft. So I know that lots of the teachers would love to take their students on, and the students would love to go, but we can't do that. So teachers, journalists, and some VIP members of Congress and their staff have been on. Oh, and Lieutenant Uhura. I was on the flight where she was a special guest. She had done decades of excellent outreach work for NASA, increasing the diversity of the NASA workforce. And so we invited Nichelle Nichols, Lieutenant Uhura from the first Star Trek, to fly, and that was wonderful. And so we invited. So she counts as a VIP for sure. Hi, I'm not hearing anything.
Hi, Dana. Lisa doesn't seem to be responding at the moment, but I think we've come to the end of the questioning,
Yes.
and the interrogation. Oh, Lisa's back now.
Sorry, I was on mute. Hate when that happens. One last question. We read about funding cuts for the program. Is that so?
That was zeroed in the budget for this current year. The White House set SOFIA's budget to zero and canceled it, but Congress restored it. So we're okay.
That's good news. Well, I think we're a little bit over time and we've reached the end of our questions. Thank you so much, Dr. Backman, for taking this time with us this evening. And thank you, Simon and at SETI for partnering with us on this event and future ones to come, and all of our guests out there with so many wonderful questions and engagement. Thanks for joining us. Just a reminder that SETI and Chabot are both nonprofit organizations, and during this time, we appreciate your support more than ever. So you can consider, please, a donation to one of our social media accounts or our websites. We greatly appreciate it. Any final thoughts, gentlemen?
I had fun. Great questions.
Awesome.
Yeah. And please, we will have a March talk coming up, and that will be advertised soon. So please do join us next month for the next SETI Institute and Chabot Talks for Families.
A couple of you asked in the chat about catching this presentation again. Yes, it will be available on YouTube. So Chabot Space is our account. Look there for this event and past ones and new ones to come. Thanks again for